All right, everyone, we are back and we are going to go through our Kroger-Vink notation problem on our practice exam. So we're working with this. I want to dope the material with this so we can form anion Frankel defects. So this is our host. This is our impurity. Let's see here, 0.8, 0.3 here. So Frankel cations will dominate. Let's write out all the intrinsic reactions. So again, we're working with this. So oxygen is minus 2, 12. So then Y is going to be plus 6. So I'm going to say null goes to a vacancy in Y minus 1, 2, 3, 4, 5, 6. 2 of them plus vacancy in oxygen, 6 of them. I'm going to also go, so Y, X goes to vacancy in Y, 1, 2, 3, 4, 5, 6, plus Y on an interstitial, 1, 2, 3, 4, 5, 6. And then oxygen, X, vacancy in oxygen, plus oxygen interstitial. There we go. How do we know that this will be essentially the dominant defect? Exponential minus delta HF over KT. So the enthalpy of fusion is really the key thing that determines which reaction has the highest concentration of vacancies. Excellent. In our Kroger-Vink notation, we know that we can put the impurity on the X. We can put a vacancy here. We also know we put the host on the Y, and we can put an interstitial here as well. And Z is the change going from Y to X in terms of the charge. So can I put a host atom on the Y? No. Can I put a vacancy on the X? Yes. Can I put an interstitial on the Y? Yes. Excellent. We need a defect reaction that incorporates a cation substitutional. So remember, we're doping it with MgO into Y2O6. So if it's a cation substitutional, it's in an Mg where my Y must be. So that's a rhyme. 6 going to 2 is going to be a minus 1, 2, 3, 4. So I need a positive reaction. I already have all of this, so I'm just going to go vacancy and oxygen. So I'm just going to put a 2 here. So we've got Mg, and let's see what we've got here. Ooh, but I can already start to see that would charge balance me, but it's not going to necessarily mass balance me because I know I need at least 2 of these. So if I need 2 Mg, so that's minus 8, right? So now I need at least 4 of these oxygens. So now I'm looking a little bit better. But I need now my 2 MgO plus 2 oxygen X. Let's see if this works. So 2 Mg, vacancy, 2 oxygen, good. Let's do my subscript because this is still minus 4. So minus 4 here, good. So how many Y's? We got 2 of them. 4 plus 2, 6. We're good. All right, let's do the next one. MgO into Y2O6. Whoops. So we got this here, done. Cation interstitial, so let's do an MgI, 1, 2. Now let's do plus a vacancy, for example, in the Y. So that's minus 1, 2, 3, 4, 5, 6. Again, we know we're going to need at least 2 of these. So 2 times 6 minus 12. I can do 6 here. So 6 MgO plus 6 oxygen X. Balanced here, there's 2 Y's. How many oxygen? 6. We're good. And then finally, anion vacancy, MgO goes to Y2O6. So let's go ahead. I need an anion vacancy, so vacancy in here. Now we already have a reaction there, but I'm going to do some, again, we need to be distinct. So I need some other negative reaction that will occur here. So I can actually see, well, I need an Mg. So how about I do this? Let's start to think. What would be a unique reaction that we can have here? I'm going to put, let's do this. Plus Mg on the interstitial, that's 2. Then I'm going to do vacancy in the Y, minus 1, 2, 3, 4, 5, 6. Whoops. I'm always getting off the edge here. 1, 2, 3, 4, 5, 6. So I know I'm going to need at least 2 of these. So now this is 2. So that's minus 12. And I just need to kind of balance these out here. So one thing I could do is I can put a 5 here. So 5 would be minus or plus 10, 2, 12. We're balanced. So I'm still have MgO plus I need oxygen X. So I'm balanced across here, my script. How many Y's do I have? 2. Oxygens, 5 plus 1, 6. That's the problem. So we'll see you in the next video. Thanks. Bye.